All right, let's start the recording.
There's any requirement, isn't it, if you follow, you didn't have anything installed?
No. I'll mention that in a second. Just waiting for these stragglers, I think. I think I should just start, I guess. All right, so welcome to the sort of what is Kubernetes talk. Just a background of me, I'm Steven Dolner. I've been a DevOps engineer for the past 6 years, and all the time been working with Kubernetes. I got a couple Kubernetes certificates with that as well. Running a small home lab, running Kubernetes in that, and yeah, that's the short background. Before we start, I do not expect you to have anything installed related to Kubernetes. But if you want to, something like Minikube or MicroK8s, there's also like K3s, very small bare bone things to start with. Do not use Docker Swarm. Just forget that exists. Just don't use it. And as always, just feel free to ask questions. So just to continue from Riley's Docker talk, we hopefully know what Docker is. We know the Docker file, how you create the Docker image, what you want to put in the Docker image, and just some basic ideas what Docker looks like when you all run it. And to really start with, we'll start with a simple Docker Compose example of a full stack app. Many people will experience like a full stack app in their developer career, and this is a good starting point about what you will run into in the Docker limitations. So if you have this full stack app, then ask yourself the question, how do you scale? How do you distribute this app to different environments like production, staging, development, or you have different variations of your app that you want to run as well at the same time. Now, obviously you can just manage every VM, every server yourself, install Docker, throw those containers on it, and you're set. But we're developers, we're lazy. We just want to chuck something at the server and just forget about it and just hope things work. So this sort of question Google engineers asked themselves, but this is around 2003, 2004, when they were still working with just VMs themselves. Docker wasn't a thing. It might have been like some idea somewhere, but all we had was the Linux chroot jails. And the Google engineers themselves just asked themselves, okay, how can we maximize performance out of every VM, and how can we scale this? And they wanted to do that because they were further developing their Google Cloud Platform. So they created Borg, obviously from the Star Trek universe. And the way Borg works is users would submit a job. Every job has a task, or one or more tasks, and these tasks are either long running or short running. Long running would be something you would present a user, like a web server, web interface, and a short run task would just be a batch processing thing. Which, to this day, Borg is still somewhat used, I think, from Google, but Docker and containers are much more lightweight than something like a VM. And when Docker got announced in 2013, the Google engineers were like, we like that. This is nice and lightweight. Borg is good, but let's do something better. So a bunch of these engineers that worked on Borg moved over to work on Kubernetes, which, say like around 2015, got sort of announced, released, and donated to the Cloud Native Foundation to make sure that people can just use Kubernetes without any drawbacks of licensing. So one of the main pain points of Docker to begin with is you have a single server that you can just throw a Docker container on, and if you want to scale that, you need to manually sort of manage that. So they took the inspiration from Borg, when you can just chuck something at it, Borg manage it, and applied that to how containers work. And that's how things were scaling. Now, I put up here with an asterisk about like those 5,000 nodes, whatever, but there's been, thanks to the rise of AI, LLMs, whatever, some of these clusters have been insanely large. OpenAI, for example, has like announced like a 7,500 node cluster, which is nothing. ByteDance moved up to like 20,000 nodes, and there has been a Google Kubernetes engine that uses up to 65,000 nodes for just AI training. And probably all these nodes are just a single item on it to train the AI on, just to move towards it. So we'll just start at the smallest of what you chuck into Kubernetes, and we'll first just look at a simple pod. The pod is the smallest workload you have in a Kubernetes cluster. And what you'll mainly see as a similarity between something in Docker Compose and a pod is your services in Docker Compose and your containers inside of a pod. You have your images, your ports that you want to expose, your environment variables, your volumes, all that stuff. But we'll template it up in a nice little pod, and we'll identify it with some labels, and we give it a nice name, and that's your smallest sort of item that you can chuck at Kubernetes, and Kubernetes will take care of the rest. We'll run your pod, and if you misconfig something, it will complain to you about that. So now we'll take this idea of a pod, and we'll think of it as a broader item. A pod can come and go. Your item can stop running. You can have a new version of it, and all that. So we'll extend it to something more persistent, something that you can iterate on or just reschedule over and over again. And we have this through deployments, stateful sets, daemon sets, jobs, and cron jobs. And what you will notice is between many of these, you'll still have the same pod template over and over again. So start with a deployment. Might look scary. All you start with is all the way in the bottom, you have a spec with your container, which is the same as we've seen before with the pod, but we say we template that. We tell Kubernetes, this is version 1 of my Nginx app. This is the pod that the template represents the pod that I want to have it run. Run it for me. And I can scale that up and down using my replicas. And when I create a new iteration of this Nginx app, I'll just reapply it, and Kubernetes will create a thing called a replica set, rolls it out, removes the old one, and you have your new version running. Which, with these couple images on the side, you can just see Currently, this is the one iteration, but once you apply this over and over again, it assigns a new hash value to it, and just creates a new hash every time, and you can see that hash value when you list your pods. Now, a deployment, as you have seen, it's messy in a way that you have a hash every time you create a pod and remove one, and when you iterate over a pod. Now, when you move to things like databases and stuff, you want something that's more, I guess, sticky. You want to know this replica of a database is there. You want to know that it's easily identified, and when Kubernetes rolls it out, you don't want a different version to suddenly appear and just be stuck there. You want to make sure everything is more the same, and that's the sort of the way that you have a stateful set. Again, you have the same sort of pod template in there, and it's more or less the same syntax as a deployment, but under the hood, Kubernetes just assigns a digit value at the end instead of this hash, and this digit value is basically the replica number of the pod from that stateful set. So if I scale the Postgres 0 up to like 2, it has Postgres 0 and Postgres 1, for example. And the nice thing about the stateful set, since it's really used for like databases, Kubernetes just allows you to immediately throw in like a volume template. I'll touch on volumes in a minute, but it allows you to easily create volumes with every replica of your stateful set, of every pod from that stateful set. Sorry. Moving on, the daemon set is more focused on making sure whatever pod you specify in that template is applied to every single node of your cluster. Now you might think, why do I want this? Well, every node is pretty stupid on its own, and it needs some helping resources to interact with the whole of a cluster. A good example are metrics exporters for your monitoring stack, or your storage, whatever storage solution you have running for your cluster. A node needs to be able to know how to interact with your storage thing. It also needs to know how the networking goes into your cluster. It needs to know how to actually join the cluster and participate inside of a cluster, which is why we have daemon sets who just make sure everything gets deployed to every node, and the whole node is able to participate correctly, and everything is running smoothly inside of that cluster. Then we move on to jobs. These are also, they're just mainly used for a one-off tasks. Think of your database backups, or basically that, like a database backup, something you want to initialize once, and then it exists in your cluster or wherever. Again, we have the template of the pod in there, and small little syntax sugar of the restart policy, which actually should be in the pod as well, just to make sure how you want to handle it when it encounters an error. But for things like database backups, you probably want to do it nightly, weekly, whatever. So we'll have a cron job, which builds on top of the job I just shown you, but then just adds a schedule to it. So then schedule to it in like the normal, I'd say, normal cron syntax. In this case, daily 2 a.m. Just simple Postgres dump. Now, I only shown like the sort of work items of a cluster. But this doesn't touch on where exactly this runs inside of the cluster. And that's how we come to things like namespaces, where you isolate your work items. Think of your monitoring stack. You probably want to isolate it and group it together inside of an item, which would be a namespace. And so the namespaces are just basically used to isolate your work items. You don't need a separate namespace for a single item. You can. I do it for a couple items you see here. But mainly you just have many different tasks that you will isolate. It's like your monitor namespace, and other items are reserved, like your kube system. That's where all the important bits go of a cluster. Don't mess with the kube system. You will have fun times if you actually do. And then basically the Kubernetes node itself. Kubernetes nodes comes basically in two flavors. You have your control plane and your worker node. Now the control plane differs in the way that it actually has some special pods running on them that interact with the decision making of a cluster. Think of how new pods need to be scheduled, how resources in a Kubernetes cluster exist, and if they need to change, stuff like that. While the worker node doesn't care about that. It just likes to be told what it needs to run and be happy with that. Now, all these nodes can just be a server itself, or you can virtualize with a VM jack.
For your home lab versus like clusters you run in production,
Yep.
do you usually make your control plane not run pods and jobs, or do you sometimes also get your control plane to do work as well?
I've done both. Personally, I prefer the control plane not to run any actually workload, but sometimes you can't get away from that. And you just have to accept the fact that your control plane needs to run these kind of workload items. Also, a good thing with these nodes is, and also the thing that why Kubernetes got created in the first place, is you want to have something called high availability. If something goes down, you want to make sure things keep on trucking. You don't want your 2 a.m. outage call. So sort of a best practice scenario would be you would have 3 or more control plane nodes, just to make sure that if something goes wrong with the cluster, like a node has a bad day, Kubernetes will just move on. Same with your deployment or stateful sets. If you just scale them up, you have high availability, and you'll be happy that stuff doesn't go wrong. Alright, so just to sort of walk back to the full stack app from the beginning. I created a namespace, chucked the full stack in it, so you can see I got the app, the backend, and the database. Also got a couple things that I will talk about in a second, called services. I got my deployments, which are my app and my backend. I got my stateful set, which is my Postgres database, and the 2 replica sets that Kubernetes created as part of each of these deployments. Now, if I something in like a development environment, I can just create 3 of these namespaces. Like you wouldn't put a production there, but like dev, staging, or like a different version altogether, and it will exist happily in this cluster. You can have different iterations of each of these items, and everything will be happy. Your developers can just work in tandem in different namespaces, and you can, basically. Here's another example. What I currently have running is as a Jellyfin stack, all my R apps, a little Postgres database in the back end, and now, so far I only mentioned things like environment variables. While we know environment variables are nice, what if we have a file that we want to mount, or some extra configuration sugar that we want to interact with and apply to our pods? So we have a config map, which is some basic non-secret values that you can do, which of course come in your environment variable key values, but also come in the form of files that you can later mount into your pod. Think of some property files, some bash scripts maybe that you want to mount in, all that kinds of stuff. Then also, once these items are mounted into a pod, if you update it outside of it, that value will propagate towards the pod, but it's the process that runs inside of this pod and container to make sure it reloads that value that got updated, which is why in a lot of use cases you'll see two containers running in a single pod. One is the actual work process, and the other one is a sort of checker to see if any of these config things got changed, and if so, it just reloads it live on the first process. And then we have secrets. Secrets basically operate the same way as config maps, but are designed for secret values like your passwords, API keys, secret files, and the way you can provide a secret value is to either set it as string data, but then when applied to Kubernetes, it gets base64 encoded, or you just directly supply a base64 string. I think there's also the binary data that you can directly upload for some scripts or executables. And so we got config for our pods, and I mentioned a little bit about storage. Now, storage is also very important, like we have in Docker, but the way we handle that in Kubernetes is slightly different. While we create a simple mount and path for your Docker Compose, in Kubernetes, with a pod, you just see where you mount it, but you also need to make sure you have an underlying system resource that will allocate or create a storage path for you. Or you can just have it still ephemeral and just throw all that stuff away once a pod restarts. So then we start with a persistent volume, which is basically what your volume will look like where all your stored items will go. So in this case, it's a big odd, but in this case it maps a specific directory, my Postgres database, towards my NAS NFS share, and it referenced back to a persistent volume claim which initiated this request. And all this volume does is make sure it's a global resource that makes sure you get your storage solution back into your pod. And then the persistent volume claim is what actually interacts with whatever storage solution you have. Jack?
What's stopping, if you have something that has like a volume mount that potentially to the replica set, like would you have that sort of thing? And like what's stopping the case of like two pods or two nodes of crashing the same volume? Would you have to sort of make sure that doesn't happen yourself, or is there stuff
Yes.
for that?
So it's right there actually in the volume claim itself. Oh, yeah, sorry. So Jack was asking what happens when two different nodes try and sort of request the same volume, and what kind of mechanism is there to stop that from happening. So the way it happens is inside the volume claim itself. So when you create a volume claim, you can specify how you want it to have access. So in this case, I have my read-write once, which means only a single node should actually be able to mount this volume and use it at a single time. Now, that's good for like a database volume, but if you have like a shared, let's say, like a shared file system, you can maybe have a like an uploader and a processor pod, and the uploader lives on node A and the processor lives on node B. You want them to actually interact with the same kind of volume. So in that case, you would set the access mode to something like read-write many. So then many nodes can read and write to the same volume. So going back to more how the volume claim works, its task sort of is to interact directly to your storage class, which in turn sort of interacts with whatever storage solution you have. So in this case, this volume claim is interacting with my NFS storage class, which is interacting with my NFS share on my NAS to make sure these database files get written to my NAS and get stored there nicely and securely. Now, in something like the cloud, in let's say AWS, you usually just mount the EBS volumes, which are block storage volumes. These are singular and can only be mounted to a single EC2 instance at one time, which is why you have a storage class which specifically says it can only be read or write once. If you have another pod that wants the same volume, it has to go on that same EC2 instance. Then if you look at EFS, which is the Amazon file shares, elastic file share system, that allows for multiple nodes to consume that same share to process these volumes on more nodes than more than one node, sorry. So then we get into the complicated bit of container networking. It's always container networking is basically magic. It interacts directly sort of with the host, how these IP tables need to be handled, and then pass it along under the hood to your Linux systems. And when going back at Borg, when it was on a single VM, this was very rudimentary. Everything had the single IP of the host itself, which made sort of interaction between these tasks impossible. But with the rise of like container networking items like Flannel, Calico, Cilium, there's probably like a bunch more. these sort of take away the magic and make sure all your containers can talk nicely to each other. And because of that, these items need to run on every node as a daemon set to make sure a node knows how to talk to another node, which is sort of following the same principles how we build up slowly towards a fully working cluster. If you deploy something on bare metal, you like your microgates cluster, you would probably by default deploy Calico or Flannel, but you can switch to Cilium if you want. But every sort of cloud provider has their own networking interface, because all these networking items need to work with whatever cloud provider has for their networking. Like Amazon has their VPCs and whatever comes with it. Google Cloud, not sure what Google Cloud and Azure have. Everyone has their own sort of flavor how these items would look like. And because of that, every pod gets their own pod IP, which makes sense. Which differs from how the Borg had that single IP. But the problem is, if you just use that same pod IP, what happens when a pod disappears? That IP is no longer available, so now your request from pod to pod no longer works. So that's why we have services, which sort of acts as a routing table for forwarding these requests to a different pod. The service IP would be more static, and whenever a pod gets created, gets removed, the endpoints of these services updates, and all your app is just concerned about is where can I find the service, and the magic of the container networking just does the rest for you. Now the service comes in 4 different flavors. You have your cluster IP, which is just the main thing you would use. This is just for your internal communications from pod to pod. You have your load balancer, which is what you would use to accept incoming traffic. With this incoming traffic, I mean stuff external to your cluster. Like if you have a web server running into your cluster, you want people to be able to reach your web server. And then you have your node port, which is like a load balancer, but it just maps a port directly from a certain node to the service itself, which, yes, it handles incoming traffic, but it doesn't do it in a load balancing way. And in many cases, using a node port is not secure at all. If you can avoid it, don't use it. If you can avoid it, don't use a node port. And then you have external names, which are basically just a CNAME. And then also for your cluster IP, there's a special case called a headless service, which just when a service is created with a cluster IP, it gets an IP. But if you explicitly set this to none, to not receive an IP, what happens if you create a headless service that way, and at this point, once you have incoming traffic to this headless service, if you have multiple receiving ends, like you have some batch processor on the end of it, the cluster networking makes sure it doesn't load balance on the end, which it does for your cluster IP. So it just throws it to whatever process it feels like, and then you will get the ingresses, which actually make sure you have URL interactions inside of your cluster. So, like going back to a web server inside of it, like Jellyfin in this case, I can go in my browser, go to my Jellyfin at home that's spiced after me, and I'll get Jellyfin. The way it interacts with this is you have an ingress controller, which controls your ingress resource, make sure that this website is available. And you hook your ingresses up with your TLS certs and all that stuff, so you have a nice. So it basically acts as your HTTP URL controller for that. So in the past couple slides, I mentioned the ingress controller, your container networks controller, in your storage, like your storage controller, which sort of brings us to what Kubernetes actually is under the hood. Usually you don't care what's under the black box, but in this case you will. So everything inside of a cluster is, except for your workloads, are like things that run in your control plane, like the name says, it's a controller. Inside of a controller, well, there's things like reconciliation loops, and inside of a cluster, every resource has its own controller, and it goes all the way down. So you have your deployment, controller. Well, deployment creates a replica set, which is a replica set controller. Then it goes down to a pod controller, and all the way down for every single resource you have. You have multiple different loops. So just to key 6 of them, every cluster needs an API server. It's your basic REST API. You do a GET request, you get your resource, you do a Postgres, whatever, you create a resource. Without an API server, you don't have a cluster. The kubelet is basically what manages a node within a cluster. And what I mean with this is make sure a node, when you create a new node, this node joins the cluster, make sure it says to the control plane, hey, I'm ready to receive workloads, what do you have for me? The scheduler, like the name implies, actually schedules all your pods. Now, you can use the default Kubernetes schedulers, but in the cloud you might opt for something else. But it always comes down to the same thing. It schedules where on when the control plane, like the API server, the controller, receives a new request for a workload like a pod. Kubernetes, the scheduler takes that request up and checks where on this cluster can I put this. And if you have something like the need for a GPU acceleration, it checks which nodes has GPU acceleration available. And once it finds a suitable node, it will just chuck it on there, and the kubelet makes sure it gets starts up and is happy. Now, the controller manager is what will run all these reconciliation loops for every kind of resource over and over again, like thousands of times a second, and make sure that what you said you want to have in a cluster actually exists inside of this cluster. So all these resources, you need some kind of persistent item on the back end, which is what you have your etcd or your dqlite, which is basically a key value storage solution for all these resources. And then you have your kube proxy, which might have a different name for wherever you have, wherever your cluster is, which is basically your container networking. So this is the basics on how a controller works. So a controller is in charge of a specific resource, and every loop it watches those resources, and every cycle it reads what resources it's tracking and checks if it's desired, like how it wants it to be and how it's expected to be. And if it isn't that way, it sends requests to the API server to, hey, update it this way, make sure it's the way I want it. And this is called the reconciliation loop, and it's applied on every controller everywhere. So a little example on that is a custom controller I made. I created this CM state injector, which stands for config map state injector, which is basically in my cluster I deploy Vault, and I also interact with AWS. I want to make sure that I have a template for Vault to use to fetch credentials from AWS, so I can like read the parameter store in there. So I got this CM state injector to make sure that every time I deploy a pod that needs this kind of credential access, the controller will just check it. Oh, this pod is created. It wants this config map. It grabs it from a template, chucks it there, and what you will see is it will have a reconciliation loop in there. Now, don't want to go too deep into what it actually does under the hood. Now, sorry, a little went a bit too far. Since I said every controller watches a resource, you can create a resource. We introduced something like a custom resource, and you can go far with this. You can go different directions with it. Some are just applicable to the stack. Some just want to order pizza. So if you write a controller that actually listens for a pizza order resource, and that controller can then actually order the pizza for you, you can have Kubernetes order yourself a pizza. And let's scroll down. You have to connect, you have to observe, you have to create, and he doesn't have to. This is the old version. I have it open. Yeah. This is mainly just an example. I went through this repo. It doesn't actually order yourself a pizza, but the idea is there. So here's the custom resource. You define yourself where the pizza needs to go, what your payment method is, and what your pizza order is. And if you actually want to create this eventually and just order yourself a pizza through Kubernetes, go for it, I guess. No. Again, I would have made. I could have maybe seen it actually work, but I went through it. It doesn't. I didn't actually deploy it and test it, but I went through the code, and it doesn't actually order yourself a pizza.
I think it's hard coded to only order blocks of code.
Yes, it is. Yeah. I was trying to. Right. Yeah. All it is set to do is just create yourself a order of a bottle of Coke, and I think it just replies back or sends a status onto that resource. It's ordered. Here's your order summary. That's all it does. But in theory, you have an API now which can order yourself a pizza by just creating this order. Now, if you combine this with your cron job, every, I don't know what time you want it, you create this cron job triggers, which then runs a kubectl command, which creates your order. Now you have a cron job that orders yourself a pizza.
Can I have an automatic order of pizza when there's an outage?
Define outage and
when my pods aren't meeting my minimum pod workloads for a certain amount of time.
so we're going to end up with like a root goal scene where you have your monitoring stack, watch whatever replica you have. Once it is not satisfied, it will trigger an alarm. That alarm triggers, it can already go, it triggers something else in your cluster, like maybe a webhook. That webhook creates this pizza order, and you have a Domino's driver at your door.
I think you go very specialized. It is the team morale operator, and it lives in the cluster, and it auto responds to outages with pizza delivered to the team.
Sounds like an adverse incentive.
Anyone want lunch? Yeah, let me take out the pod real quick.
Or if Cloudflare sneezes, maybe you can still order a pizza.
If the pizza order fails to get submitted, does that then count as the process still being unhealthy? Therefore more pizza gets submitted?
So that ties back to how good your coding skills are. Because what Kubernetes sees is you created this order, but you as the developer of this controller need to make sure you handle what happens when your order doesn't get fulfilled. Do you retry it over and over again? Do you just accept it and just spit the status back, hey, I couldn't order? Maybe try a phone or carrier pigeon? Does anyone have any more questions? Maybe not specifically to a pizza cube. I don't see any questions. Okay.
You talk about the cluster and the rebuild for a certain contract. Because it's a good story.
Oh God. So, a couple years ago, the December of 2023, I was contracted by a local company that's right across the road there called Secor. They wanted a lovely AWS EKS cluster. It had to be in a specific environment because they wanted to make sure all their data only exists in a certain country. Now, AWS is big, and AWS has availability zones. These availability zones in a region could span multiple countries or not the country you want. They also have a thing called local zones, which would sort of bring your AWS resources very specifically to a certain location. In this case, it was luckily that certain country we wanted the data to be in. What AWS sort of doesn't tell you is what's available inside of a local zone. And normally when you deploy an AWS EKS cluster, you'll throw in a load balancer, like you have a network load balancer, application load balancer, whatever. You just throw at it and you have your web request coming into your cluster. This doesn't exist in a local zone. So the only option we were left with are these node ports. Where did I have it? So the only option I was left with was were these node ports. But then we still have the issue, your web requests don't actually work. You need some magic through, in this case, Route 53, to sort of you need this magic through Route 53 and some external DNS controller to sort of magically create these web addresses coming into this node port only specific cluster. And yeah, that's basically the whole headache of that.
Even pulled some magic for us. It was very good.
I wish I could show that, but I don't think they would like that. Let me just pull up the repo and just share the code base.
I think the point of this as well is that previous to being deployed on Kubernetes, the application we had was deployed to Google Cloud using like high-level like Cloud Run and stuff. So it was interesting that it gave us an option to sort of go from a very like high-level tool to a low-level tool. So like we literally could not. There was no cloud provider in insert country here, so we had to go with this low-level approach. But our application, which still sort of, doesn't have to care about provisioning, was still able to be sort of ported from like, nice does it for you Google Cloud to like low-level Kubernetes, and that was very.
Yeah. So also in this case, this solution went from basically serverless to not serverless, and actually we ran into the issue where we used up all of the available EC2 instances of that local zone, which was a fun bug we found. We literally got the message in the schedule saying, sorry, can't fulfill your request. There's no more instances.
So, look at this. Maybe it's there. I just missed it. I'll use Jellyfish as or actually, it's on our front. It's a sit for a second. It's on our depends on all the is there anything within your service or these templates that like say, don't try to do this until you know a Postgres database is available or another service?
So, no, not in the service direct. So what Tim is asking is, yeah, what Tim is asking is, if you have a service that relies on another one, does the service itself try and see if that other service is available before it actually sends a request, or do you need something else for that? And the answer is you need something else for that. So if you, in my case, Sonar does depend on the Postgres database. I configured to use Postgres instead. But what you would usually see is if you start up, you will configure your pod to have an init container. I might have just skipped over that entirely when I talked about pods. Let me just scroll back all the way. Yeah, I just briefly got it there, but so your pod can have your containers, which run whatever life cycle you have of your pod, and you have init containers, which sort of prepares your workload for when it needs to run. So in this case, you can have a health check in your init container to see, hey, is my Postgres up? Is my Postgres up? And continues until that's done, and then the init container finishes, and the rest of your pod continues to start up.
I think that, to be fair, something like that, version.
Yeah, it has to depends on.
And
Yeah.
download is garbage anyway, so it's still actually
Exactly. Yeah. It's just sort of the Docker compose depends on is just like, hey, it started, but if it's in an error state, it's not healthy. So, what if you have other pods that depend on, like in this case, my Postgres? If my Postgres is in a corrupted dead state, all my other services would start up in Docker compose and then crash and complain about that Postgres is not available. Whereas if I have these init containers, it will just be stuck in a pending state, or sorry, in its state, because my Postgres is dead.
Remember how with a deployment, your pods can kind of end up on whatever node, and you get into persistent storage lanes. Is the stateful set different in that sense, in terms of like, will the storage just disappear if it's destroyed recreated?
No, so that also ties into your retention rules of whatever volume you create. But if you delete a stateful set, if you set that in your claim template, hey, delete the storage as well, yes, the storage gets deleted. But if the pod just moves from one node to another, the volume can just move with it, which is how whatever storage solution you have, that controller will actually do that for you, or sort of asks whatever thing you have to do it for you. So, most likely, if you deploy a specialized controller for it. So, a lot of things you can see in Kubernetes, sort of, if you want something custom, deploy a controller that does it for you. So, for example, let me see if I can pull it up. I think this would just fall back more to like external DNS and how that interacts with Route 53. You can deploy external DNS to like a cluster, and when you create an ingress resource, it takes that URL and probably chucks it at Route 53 to make sure your DNS is configured for that.
I just Googled it. Azure provides a controller for exactly that purpose.
Yeah.
So you can point it at Azure App Config Service, and it will create config maps from the configuration.
Thank you. Something like HashiCorp Vault, to manage your secrets, you can have Vault pull secrets from wherever as well, and then together with like with an external secrets operator, creates these secrets for you, and now you have your secrets living in Kubernetes as well. And if you update it to your cloud, eventually it makes its way down into your Kubernetes pod.
For people here today who are potentially beginners at this stuff, what would be your recommendations for ways to go about learning Kubernetes and resources and such?
So you can start by probably installing something like microcreate, something that just runs on your laptop. Don't deploy on a cloud provider unless you have too much money and don't care about money. Please. So when you just install microcreates or minikube, whatever, onto your laptop, it just creates a single node for you, and then just try and deploy a simple pod, and then build out to like full stack environment. And you can read the wiki as well, but it's a bit dense and could be a bit more convoluted to get through. But I'd say the best thing to do is just start small with a simple pod, delete it a bunch of times, poke at it, break it, fix it over and over again, and then just build up to your full stack example. Anyone else?
Yes. Okay. You mentioned something about doing some so what also applies to custom resource provision?
Yes. So when you want something outside of what Kubernetes ships with you, and you install like a custom controller, or it will always ship like a custom resource with it. I didn't go into it because it's a, I guess, more complicated topic which you probably will never touch. You might just see in passing, but that's your custom resource definition, which comes back to here the pizza order. Is it in the API section? Not actually sure where they have it. Where am I? Where did that go? Yeah, so in this case, for my operator, you have this resource definition. You do not write this by hand. This is like, luckily this one is only 140 lines, but some of them go up to thousands of lines. You don't write it by hand, you have something generate that for you, but that basically specify what you have, how it is defined, and all that to tie back into the controller code itself as your, in this case, like up there to my API types into a Go struct, for example.